No, James Webb didn't disprove the Big Bang. Carbon dioxide found in an exoplanet atmosphere, an amazing picture of Jupiter from Webb, pieces of other stars found in an asteroid, weak astronauts arriving on Mars, and a new way to measure distance in the universe. All that and more in this week's episode of Space Bites. Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years. This is our Space Bites segment, where we cover all of the breaking space and astronomy news that's happening this week. Let's get into the news. No, James Webb did not disprove the Big Bang. Now, I've been getting a lot of emails from many of the people who follow the work we do, comments on YouTube, references on Twitter. I get it. You've seen the story that astronomers are saying that James Webb has disproven the Big Bang. And you're wondering, is it true? Is the Big Bang a myth? No. James Webb did not disprove the Big Bang. Now, James Webb found some really interesting stuff, and it's helping to provide some information about a time of the universe's evolution that was poorly understood, but it is all fitting nicely within the previous theories. Now, the Big Bang has three major pillars of evidence. The first pillar of evidence is that everywhere we look, galaxies are moving away from us. The faster they are, the farther away they are. And so no matter where you could go into the universe, if you looked in all directions, you would see galaxies moving away from you in all directions. And so if you roll the clock backwards, you can imagine a time when all those galaxies were closer together. That's like the first pillar. The second pillar is the fact that we see the cosmic microwave background radiation. This is this diffuse glow in all directions in the universe. And if at one point, if you had all of those galaxies that were moving away from each other and they were all so packed together that they were effectively the surface of a star, that the entire universe was the surface of a star, it would give off radiation that perfectly matches the cosmic microwave background radiation. And the last pillar is the amount of hydrogen versus helium in the universe. And so if you roll the clock back even further, you get to a time when the entire universe was like the core of a star, like the core of our sun, and it was fusing hydrogen into helium for a few minutes. And the ratio we find of hydrogen to helium in the universe today, as well as lithium and other trace amounts of other elements, perfectly match that the universe was once the density of the core of a star. And so at one point, the universe was as dense as a star. At one point, the universe was as dense as the surface of a red star. And then at one point, the universe was dense enough that galaxies were very close together, but moving away from each other. And so this makes this very smooth description of a universe that is expanding. But there are gaps in the knowledge. We don't have a lot of information between the time when those first galaxies had formed and that time when the entire universe was like the surface of a star. And James Webb is perfectly designed to explore that time frame. It's able to look at galaxies as they appeared just hundreds of millions of years after the Big Bang. And so we can see how mature do these galaxies look, see the dwarf galaxies starting to come together, and maybe if we're lucky, even see the first stars as they were forming. The exciting thing about James Webb is it really is starting to help confirm this idea that galaxies were more mature, more large, fully formed at an earlier time in the universe than astronomers had ever thought before. So why is this? Well, astronomers still really don't know. They're trying to study the early evolution of galaxies in the universe and try to understand how they came together. Did galaxies just collapse out of giant regions of gas and dust directly into the full galaxy? Or do they form from smaller dwarf galaxies and merge together? Were there primordial black holes left over from the formation of the universe that then served as the anchors of these larger galaxies so they could come together more quickly? More research is necessary. And James Webb is perfectly designed to look into this time and be able to see these early galaxies starting to come together and should provide a lot of the answers that astronomers are looking for. And of course, as always, generate new questions. And so you have a bunch of people who have theories that are attempting to overturn the Big Bang. And every time there's any kind of controversy in cosmology, they come forward and say, see, our ideas were right all along. But the problem is that those theories have been debunked sometimes decades ago. They made predictions that don't match the observations. And so those theories have to be discarded. And yet they haven't been discarded. And so the people who came up with those theories continue to hold on to them, continue to bring them out, continue to try to look for any crack in the armor of the Big Bang cosmology and use it as a chance to show that the whole thing is a house of cards and it's coming down. And when you see information coming out of the media, but not coming out of the scientific community, you should be skeptical. You should be curious about what is the source of this information? What is their agenda? What is their objective? So I'm, of course, just a journalist, but we had a great article on Universe Today from one of our PhD astrophysicists, Dr. Brian Koberlein, and he went into this in much more detail, laid out the evidence, explained why, no, it doesn't overturn the Big Bang, and can give you a lot more information so you can dig into this more deeply. And so one of the pieces of information that these Big Bang debunkers are using is that they're saying that there was a paper that was titled Panic at the Disks, First Rest Frame Optical Observations of Galaxy Structure at Z greater than 3 with James Webb in the SMAC 0723 field. And they were focusing on the word panic, but Panic at the Disks is a pun on the band Panic at the Disco and has nothing to do with about panicking and more about coming up with a clickbaity title for your scientific paper so that people will read it. And mad props to them for including a pop culture reference in their paper. I wish more scientists would be a little more whimsical, a little more silly, a little more readable, a little more accessible to the general audience when they come up with titles for their papers so that I, as a journalist, when I'm looking through them, will go, oh, that's a clever title. I wonder what that paper's about, and then read it. So more of that, please. So don't panic. Nobody's panicking. Enjoy the science as it continues to unfold over the next years, decades. Carbon dioxide discovered in an exoplanet atmosphere. This is a huge piece of news that just broke this morning, so we're still kind of digesting it here at Universe Today. But, of course, we know of more than 5,000 exoplanets that have been discovered using various techniques. And up until this point, all we know about these planets is their distance from the star, the mass of the planet, the radius of the planet, how long it takes to orbit around the star. But that's not much. I mean, that'll tell you that the planet is in the habitable zone of the star. It'll tell you if it's completely inhospitable, if it's bigger than the Earth, smaller than the Earth, is it kind of like Jupiter? We don't really know much more information. The next phase in studying exoplanets is to observe their atmospheres, to try to get a sense of what they're made up of. When you think about how we explore planets here in the solar system, we know that Venus has a hellish atmosphere that is almost entirely carbon dioxide. Mars has a very thin atmosphere, but also of carbon dioxide. Jupiter has a different atmosphere, the ice moons, etc., and the Earth, of course. And astronomers have used James Webb and its ability to observe exoplanet atmospheres with more precision than anything that's ever come before. And they were able to see carbon dioxide, a very clear, unambiguous, no question, there is carbon dioxide signal in the atmosphere of a planet called WASP-39b. Now, don't get too excited. WASP-39b is like the mass of Saturn. It's considered a hot Saturn, so it orbits very close to its star. So imagine Venus, but the mass of Saturn, very hot, very inhospitable. But the fact is that James Webb was able to see this really clear, strong fingerprint of carbon dioxide in the atmosphere of this planet is really exciting. You're probably wondering, how did they do it? When a planet passes in front of its star, astronomers are able to see the way the light from the star dips. But with a telescope like James Webb, they're also able to analyze the chemical fingerprint of the star during this process. And so what they do is they measure the fingerprint of the star itself, and then they measure the fingerprint while the planet is passing in front of the star. And they're able to tease out the signal that is just coming from the planet's atmosphere as opposed to the star. And they were able to see this. Now, this is just the beginning. You can imagine in the future, astronomers are going to be able to find other gases in the atmosphere of these planets. Maybe they'll find nitrogen, maybe they'll find methane, other things. And so some of these will eventually become biosignatures that we may be able to know that there might be life on some of these planets. So this is a really exciting observation, and it's just going to be one of the first of many coming up where we're going to learn more and more about exoplanets. So it's funny, this, like, two of James Webb's main jobs delivering science information this week. It's been great. Jupiter by Webb. All right, it's all Webb all the time today. I'm not going to save all the Webb images to the end. Let's lead with them. And so we've got this incredible image of Jupiter taken by Webb. And actually, we've seen versions of this picture before, even with the first image release. Astronomers had turned Webb onto Jupiter and were able to capture some images of the planet in infrared. But what's cool about this is that people have had time to process these images, really look at them, really tease out the data. And this is by far the best version of that picture that I have ever seen. Of course, this was done by one of our friends, Judy Schmidt, who you can see on Twitter. She's Space Gek. And she has been really one of the main people behind all these really cool images of James Webb. She goes onto the raw James Webb data server, pulls the images down, and works with them until we can see them visually like this. And what's cool in this picture, you can see the auroras at the top and the bottom of Jupiter. You can see the rings as this very faint, almost ghostly shape around the planet. And in infrared, the lighter colors correspond to warmer temperatures on Jupiter and objects that are of sort of higher altitude. And so you can see how the great red spot is slightly warmer, and you can see some of the higher altitude hazes on Jupiter. It's an incredible picture and very scientifically interesting. And in this case, the scientists have been working with Judy to pull out this data so they can better understand the weather conditions and auroras on Jupiter. Black holes help measure distance in space. Astronomers have many different ways to measure distance in the universe. For close distances, say within a few thousand light years, astronomers can use parallax. That's what the Gaia mission is really good for, using astrometry. At medium distances, astronomers use Cepheid variables. This is what Hubble used to measure the expansion rate of the universe. Farther than that, astronomers use Type 1 supernovae, and at the greatest distances, astronomers use redshift to measure how fast the universe is moving away from us and how far away things are. But they're always looking for any kind of way to measure distance to add on top of this. They call this the distance ladder. And the ideal is that the different elements of the distance ladder will overlap one another. And so you know that the parallax method and the Cepheid variable method overlap one another, and so they can double check each other's accuracy. And now astronomers are proposing a new way to measure distance in the universe using colliding black holes. So when you think about two black holes that are colliding, when this happens, they are generating gravitational waves that propagate through the universe, and we're able to detect them with the LIGO observatory. Just like light redshifts as it moves through the universe, gravitational waves redshift over long distances as the universe is expanding underneath these gravitational waves. And the impact is that it makes the merger look slower, as if the black holes were merging with more mass than they actually did. And so it's kind of tricky to then reverse engineer and try and figure out, if you see the gravitational waves, what was the mass of the two black holes if you don't know exactly where it happened. And so over time, as astronomers see more and more of these black hole collisions, they're going to be able to map out the standard kinds of collisions that happen and know what the actual masses were, and then what they're redshifted to by the expansion of the universe, and use that to figure out how far away that black hole collision was, and then use that as a way to measure the distance to the galaxy that the black holes were in. So another possible way to measure distance in the universe, which is great. Astronomers can't get enough of these. The more they can find, the more accurately they can measure things in the universe. Ryugu samples are partially interstellar. Thanks to Oumuamua and Borisov, we learned that interstellar asteroids and comets are passing through the solar system from time to time. But is there any geologic record of any kind of interaction with the solar system and particles that came from outside the solar system? And it turns out yes. During the Hayabusa 2 mission, they brought back samples of asteroid Ryugu. And when they looked at those samples of the asteroid, they were able to find grains of dust that came from outside the solar system. So when you examine any meteorite, you find that they all share the same origin. The same isotopes of radioactive elements in them give a fingerprint for the fact that the solar system formed about 4.5 billion years ago. Every meteorite that you find the same formation time. But astronomers have found occasional grains of material that came from outside the solar system that are older, that have an isotope ratio that is older than the solar system. And in this case, they were able to find a bunch of these grains in the samples from asteroid Ryugu. And so where did these come from? And the idea is really cool, that before the formation of the solar system, the sun was in a stellar nebula with hundreds, possibly thousands of other stars. Some of these stars were small, like the sun, but others were these giant, hot stars, the kinds of things that Betelgeuse was, the kinds of stars that we see in the Orion Nebula that are so bright and carving out these giant cocoons of gas and dust. And these powerful stellar winds that are coming off these hot stars are filled with grains of dust that are coming from these stars. And so this dust reached the solar system, the solar nebula, and they were deposited inside various asteroids that are then being found by astronomers today. And so astronomers can find lots and lots of these little grains and then use that to reverse engineer what the larger nebula that the sun formed within and try to get fingerprints of the other kinds of stars that were around us. It's amazing. Will astronauts feel weak when they arrive on Mars? Now, we know that a journey to Mars is going to be dangerous. You've just got the lack of atmosphere, you've got the high velocity, you've got the landing. Mars eats spacecraft for breakfast. But over the course of the 6 to 7 months it's going to take astronauts to get to Mars, they're going to be in microgravity. They're not going to be experiencing normal Earth gravity. They'll be exercising, they'll be trying to keep their muscle tone, but at the end of this trip, they're going to then have to set foot on Mars, and they're going to have a lot of work to do to keep themselves alive to deal with the cold temperatures and lack of atmosphere and the radiation on Mars as well. And so a question that some researchers had was, will they be strong enough? Now, we know that when astronauts come back to Earth, they're very weak, especially if they've been in space for months, in some cases more than a year. They have to be carried. They have to sit in a wheelchair. If they stand up too quickly, they get very dizzy and can faint. And imagine if astronauts got out of their spacecraft on the surface of Mars and they all fainted when there was work to be done. How long will it take them to build up their strength? So researchers went through historical data, looked at the amount of time that the astronauts spent in space, looked at the loss of their muscle capability when they came back to Earth, and then simulated what it might be like for them if they got to Mars. And the good news is they should be fine. When you travel in space for 6 to 7 months to get to Mars, and then you're now in Martian gravity, which is about a third the gravity of Earth, you'll probably have enough strength to be able to carry out your duties and rebuild your muscle mass and rebuild your overall capability to carry on your mission and not faint on the surface of Mars. So good news. If any astronauts are listening, you will probably be able to go to work on Mars and not pass out. There's less water under InSight than scientists expected. The exploration of Mars is often about the search for water on Mars. And we know there's water on Mars. I mean, the polar ice caps are made of water, and water has been found under several hundred meters of regolith. It's been found closer to the surface, but it's mostly in the polar regions of the planet. Wouldn't it be great if there was some kind of water ice somewhere near the equator, which is also where the most comfortable temperatures are for people who are going to be exploring Mars? Now, NASA's Mars InSight lander is near the equator, and it kind of has the ability to search for water under the surface. It has a seismometer on board, and so it can detect seismic waves passing through the planet and be able to detect if those seismic waves are moving through water. And so researchers have looked through some of the data collected by Mars InSight, and from what InSight can tell, there's no water under its feet, down to a depth of at least 300 meters. Now, it could be deeper, but Mars InSight can't find it. Now, that could just be one sample, one place near the equator. There could be water in other places, but really, to get water on Mars, you're going to have to move towards the poles and away from the equator, towards the colder, more extreme temperatures, away from the warmer, more comfortable temperatures. So hopefully people will find some water, but Mars InSight says it's going to be a tough search. Even though I'm on hiatus, we were able to record a couple of really cool videos this week. The first was an interview that I did with United Launch Alliance's CEO, Tori Bruno. It was great. It was a fantastic conversation with Tori, talking about just the history of the company, of the current state, and of course, what's happening with its Vulcan rocket system, which is going to be its entirely new system. What are the impacts of the Russian war in Ukraine to the rockets that they're already flying, and sort of what is his long-term vision for the future of humanity in the solar system? So if you haven't already seen the interview, it was great. I really enjoyed doing it, and I think you'll really like it too. The second video that I did was kind of silly, and this was a conversation that I had with my producer, Anton, where we had been playing with this artificial intelligence software called Midjourney to be able to generate interesting images of space. And I made a bunch of food space pictures, and Anton made a bunch of car and cat space pictures, and it's fun and a really interesting look at the capability of artificial intelligence as a way to generate images today and a hint of what might be coming in the future. So check that out. The other big piece of news, of course, is that NASA's Artemis 1 mission is expected to launch on August 29th. So hopefully next week when we record Space Bites, we will be able to include that in the news. But maybe we'll do something separate just for that launch if it's interesting enough. So stay tuned for that. And of course, we are out of hiatus at the end of August, so live streams are coming back in September. Stay tuned for that. Now, if you want more information on any of the stories that I talked about today, of course, they're in great detail on the Universe Today website. So all of the links are in the description down below. This is a smaller version of my weekly email newsletter that I write and goes out every Friday to 55,000 people. It's completely free. There's no ads in it. I write every word. You should definitely check it out. Go to universetoday.com/newsletter to sign up. And did you know that you can also get all of our videos in an audio format? Just go to universetoday.com/podcast or just search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And this week, I've got a 90-minute long interview with me that was on another podcast. So definitely, if you want to hear some additional content that you can't find anywhere else, check out the Universe Today podcast. Thanks to everyone who supports us on Patreon and allows us to remain independent. If you want to join that amazing group, go to patreon.com/universetoday. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Andrew M. Gross, who supports us at the Master of the Universe level. All your support means the universe to us. All right, those were all the stories this week. A lot, I know, it's been a big week, and we'll see you next week.